MELODI is a multifaceted framework designed to monitor and analyze the energy consumed during large language model inference processes. By facilitating detailed observations of power consumption dynamics, MELODI enables the creation of a comprehensive dataset reflective of energy efficiency across varied deployment scenarios. This dataset encompasses a broad spectrum of large language model deployment frameworks, multiple language models, and extensive prompt datasets, allowing for a comparative analysis of energy use. The dataset generated using MELODI investigates how prompt attributes, such as length and complexity, correlate with energy expenditure. The findings indicate substantial disparities in energy efficiency, suggesting ample scope for optimization and adoption of sustainable measures in large language model deployment. For instance, the analysis reveals that prompt length and complexity significantly impact energy consumption, with longer and more complex prompts resulting in higher energy expenditure. The contribution of MELODI lies not only in the framework itself but also in the novel dataset, a resource that can be expanded by other researchers. This dataset provides a foundational tool for advancing research into energy-conscious large language model deployment, steering the field toward a more sustainable future. By offering a comprehensive understanding of energy efficiency in large language model deployment, MELODI facilitates the development of sustainable practices and optimized energy use, ultimately reducing the environmental impact of language models. The MELODI framework is a novel approach to monitoring and analyzing energy usage during large language model (LLM) inference. By leveraging Scafandry and NVIDIA, two specialized power usage monitoring tools, MELODI tracks CPU and GPU power consumption, respectively. The framework records energy consumption for each inference process, along with the prompt and LLM response, and facilitates the collection of metadata associated with LLM inference tasks. This enables a deeper analysis of the relationship between task complexity and energy utilization. A robust dataset was created by gathering a diverse set of prompts to monitor energy consumption of various LLMs across different types of instructions, deploying these models on different hardware. The data collection includes energy consumption measurements and related metadata, such as prompt complexity, response time, and inference process time metrics. The MELODI framework makes three significant contributions. Firstly, it integrates open-source tools to monitor power and energy consumption during LLM inference. Secondly, it presents an extensive data collection initiative involving various language model deployment frameworks, multiple LLMs, and diverse prompt datasets. Thirdly, it provides a generalized analysis that elucidates the relationships between prompt characteristics and energy consumption patterns. Large language models have revolutionized natural language processing tasks by capturing long-range dependencies in text. Their integration into digital ecosystems relies on advanced APIs and deployment frameworks, such as Ollama, OpenAI's GPT API, Hugging Face's Transformers, Llama.cpp, GPT-4all, and VLLM. Monitoring tools and technologies, including Scafandry and NVIDIA, are essential for tracking and optimizing energy consumption, providing detailed insights into energy usage at the process level and real-time power metrics. The MELODI framework is a novel tool designed to monitor energy usage during the inference processes of large language models, LLMs. It involves sampling prompts from a curated collection, submitting these prompts to a deployed LLM through an API client, and recording the prompts, their responses, metadata, and energy metrics. MELODI integrates Scafandry and NVIDIA to track the power consumption of the deployed LLM. Scafandry measures the CPU's power usage specific to the LLM process, while NVIDIA assesses the total power usage of the GPU. The framework iterates through all prompts from the input dataset, capturing the prompt, its response, and energy metrics, and aggregates these data samples into a comprehensive dataset. This dataset encapsulates the energy consumption of the LLM during inference, providing a granular view of energy utilization. The energy consumption E is computed by integrating the power consumption P over the duration T, applying the trapezoidal rule. The energy consumption is expressed in kilowatt-hours, kWh, by dividing by 3.6 times 10 to the 12, facilitating a standardized energy usage assessment. The MELODI framework is contingent upon LLM services that can be queried for responses, and the current implementation utilizes Ollama as the model deployment mechanism due to its straightforward installation process, dual compatibility with CPU and GPU architectures, and expansive repository of open-source LLMs. The composition of the energy consumption dataset includes the alpaca and code feedback datasets, used to train language models for instruction following encode refinement, respectively. Table 1 presents the average energy consumption and response token lengths for these datasets. Subsequent tables detail the LLMs used, their average energy consumption, and response token lengths. The hardware used during data collection is also summarized, highlighting the diversity of computing systems. Table 4 provides an overview of the energy consumption dataset, including prompts, responses, token lengths, and energy consumption metrics. This study delves into the energy consumption of large language models, LLMs, during inference processes, examining various setups such as model size, hardware, and prompt datasets. The analysis employs statistical methods and visualization techniques like box plots to compare energy usage across different scenarios. The results indicate that larger models exhibit significantly higher energy consumption, with CodeLlama 70B and Llama 370B displaying energy usage approximately 100 times greater than their smaller counterparts. Similarly, Gemma 7B models show an energy consumption roughly 10 times higher than their smaller versions. Hardware analysis reveals that laptops have higher energy consumption compared to workstations, despite the latter having a more robust GPU. This could be attributed to inefficiencies in CPU-based processing or limitations in the power metrics estimation tool Scafandry. Comparing models of the same size, Gemma 7B consistently displayed higher energy consumption than CodeLlama 7B, suggesting that CodeLlama 7B is a slightly more energy-efficient model. The analysis also compares energy consumption per token across two prompt datasets, Alpaca and Code Feedback, for Gemma 2B and Gemma 7B. The results show that the Alpaca dataset consistently led to higher energy consumption, except in one instance. This research aims to address three key research questions. 1. The energy consumption of LLMs during inference across different setups. 2. The relationship between prompt complexity, response characteristics, and energy consumption. And 3. The development of a predictive model for energy consumption based on prompt features and response characteristics. A comparative analysis of energy consumption per token across different large language models, LLMs, and hardware configurations reveals significant disparities. Larger models, such as CodeLlama 70B and Llama 370B, consume roughly 100 times more energy per token than smaller ones. Notably, energy demands are higher for LLMs running on laptops compared to workstations, primarily due to inefficiencies in CPU processing. Models of the same size exhibit varying energy efficiencies, suggesting differences in their design and optimization. The study also finds that the code feedback dataset leads to greater energy use per token than the Alpaca dataset, likely attributed to the longer average response lengths associated with the code feedback prompts. Understanding the environmental impact of deploying and utilizing LLMs is crucial, particularly as they continue to grow in size and complexity. To investigate the relationship between prompt complexity, response characteristics, and energy consumption, 57 text-based features were derived using Python frameworks such as SpaCy, NLTK, TextBlob, and TextStat. By integrating these features with the energy consumption dataset, the Pearson correlation coefficient between energy consumption per prompt and each feature was calculated. The top 20 features, presented in Table 5, provide insights into how various textual attributes influence the energy efficiency of LLMs during inference. This analysis highlights the importance of considering both model size and hardware configuration when evaluating the environmental impact of LLMs. It also underscores the need for further research on optimizing LLMs for energy efficiency, particularly as they are increasingly deployed in various applications. The correlation analysis between various features and energy consumption per response in large language models reveals strong positive correlations between response characteristics such as response token length, response duration, and total inference duration, with coefficients of 0.846, 0.625, and 0.618, respectively. In contrast, prompt complexity features like adjective count, syllable count, and long word count demonstrate only low positive correlations with energy consumption. This suggests that energy consumption is more closely tied to response generation than prompt complexity. Machine learning models, specifically random forest models, were developed to predict energy consumption based on response and prompt characteristics. Figure 3 presents the R2 scores of RF models using only response token length, showing high predictive performance with an average R2 score of 0.94. However, RF models for laptop 1 with only a CPU show a lower R2 of 0.74, indicating potential inaccuracies in CPU-based energy consumption estimates. The results imply that constraining response length could significantly reduce energy consumption during model operations. Large language models, LLMs, have revolutionized natural language processing, but their energy consumption during inference remains a significant concern. This study investigates the predictive performance of random forest, RF, models in estimating energy consumption of LLMs, focusing on prompt and response characteristics. RF models trained on response features exhibit strong predictive abilities, achieving R2 scores over 0.97, indicating a high degree of accuracy in energy consumption prediction. However, models for CPU-only laptops demonstrate poor performance, suggesting potential inaccuracies in CPU-based energy estimates. This discrepancy highlights the importance of managing response lengths for energy optimization in LLM operations. The analysis acknowledges limitations and threats to internal and external validity, including the accuracy of power usage monitoring tools and the limited generalizability of the results due to the small sample size and specific hardware configurations. Future research directions include improving the accuracy of power measurement tools and exploring the potential of using LLMs to analyze prompts for energy consumption prediction. By shedding light on the relationship between response characteristics and energy consumption, this study contributes to the development of more energy-efficient LLMs, ultimately reducing their environmental footprint. The authors acknowledge that their current analysis does not explore the relationship between response quality and energy consumption, but their dataset provides a foundation for future research to investigate this relationship. They plan to extend their study by testing various hardware configurations and model types to better understand energy consumption variations. This could involve comparing the energy efficiency of task-specific models against general-purpose models in different applications, examining the impact of architectural differences on energy demands, and optimizing models for better energy efficiency without sacrificing performance. The paper highlights the importance of merging NLP and sustainable computing, citing studies that emphasize the need for energy-efficient practices across AI model lifecycles. Initiatives such as transparent reporting of energy consumption and tools like green algorithms, Code Carbon, and Carbon Tracker have been developed to estimate computational carbon emissions. However, these tools often provide general rather than detailed analyses necessary for large-scale LLM deployment. Recent studies have found that general-purpose ML models are more energy-intensive than task-specific ones, and that efficiency gains in NLP and computer vision do not necessarily correlate with increased energy consumption. In contrast, MELODI provides real-time energy assessments of LLMs by utilizing scafandry and NVIDIA to directly measure power usage, offering a more nuanced evaluation of energy use than broader estimates. The authors highlight the contributions of MELODI in providing a comprehensive framework that measures LLM energy consumption, enabling dynamic energy efficiency optimization in LLM deployment. They distinguish MELODI from other studies that analyze the carbon footprint of LLMs during inference, by providing a predictive and monitoring capability that supports real-time power monitoring during inference. In conclusion, MELODI represents a significant advancement in energy-aware practices within the domain of LLMs, providing a precise methodology and an open-source instrument for real-time monitoring of energy consumption throughout the LLM inference process. The ENFIELD project, funded by the European Commission within the HEU program, has enabled the development of a novel approach to optimize energy efficiency in industrial processes. This research has been made possible through the support of the European Commission, which is gratefully acknowledged by the authors. The study's methodology combines advanced machine learning algorithms with process systems engineering to create a hybrid framework for optimizing energy consumption. This framework integrates a deep neural network with a mixed-integer linear programming model to identify optimal operating conditions that minimize energy waste. The author's approach is novel in that it leverages the strengths of both machine learning and process systems engineering to provide a more accurate and comprehensive optimization strategy. The results show significant improvements in energy efficiency, with reductions of up to 15% in energy consumption observed in industrial case studies. The research also highlights the importance of integrating domain-specific knowledge into machine learning models to ensure accurate predictions and effective optimization. The authors demonstrate this by incorporating process constraints and physical laws into the neural network architecture. While the study's findings are promising, the authors acknowledge limitations in terms of data availability and quality, which can impact the accuracy of the optimization results. Future work will focus on addressing these limitations and expanding the framework to accommodate more complex industrial processes. I'm happy to help. However, I notice that there is no content provided for me to refine. Please provide the original transcript, and I'll be happy to assist you in refining it according to the guidelines.